So welcome everyone. We are very excited to be here today and share the results of our work. This has been a one-year project with a little bit of an extension, and we got quite a bit done. First, I would like to acknowledge my team here. Gopal and Jim were great collaborators, and we had a lot of fun working on this project. And today you'll hear from all of us presenting this work. I would also like to make some acknowledgements in the very beginning. First of all, WRC for funding this work. Thank you so much. This was very impactful, and without this support, we could not have done this project. We had several undergraduate students working on the project. On our campus, we don't have many graduate programs, so we rely on undergraduate students working with us. And usually these projects are highly transformational for them in their educational career. The three students who were our research assistants were Violet, Josh, and Colin, and they came from both the environmental science and the new civil engineering program on our campus. We also had Rhonda working in the summer with us for a brief amount of time. She was supported by a summer research fellowship through an alternate funding source, and she was a student at Green River College, one of the local community colleges. Additionally, we are very grateful to Dr. Joan Hardy for all her expertise in public health and all the conversation that helps us shape this project and put it into perspective. And last but not least, all the sources for existing historic field monitoring data that we took advantage of to validate our model, specifically Will Hobbs at the State Department of Ecology, Snohomish County for their field monitoring, lake monitoring data, and Brian Molman at Pierce Conservation District. So let's start with the problem statement. As many of you might know, harmful algal bloom events, or for short for that, HAB events, in lakes and reservoirs are an increasing issue nationwide, and it's the same phenomena happening here in the state of Washington. We are experiencing an increased number of these events, and we also see an increase in the toxicity associated with these events. One of the issues associated with that is that the species that cause these events are often invasive, and they can easily adapt to changing conditions. And there are many drivers that cause these changes, including natural and anthropogenic drivers. Climate change is a big one. And then, of course, any activity associated with adding additional nutrients in these environments. So in the state of Washington, for those of you who are not from this state, has what we call an opportunistic monitoring program, which is not structured monitoring, but rather when there is an event noticed by someone, that's when sampling takes place. And what we have seen is that there is an increased number of events when guidelines, our guidance levels are exceeded. And let me show you some data for a couple of lakes. For example, Lone Lake in Island County. This is a 90-acre lake on Whidbey Island and has a history of toxic bloom events. What you see here is an 18-year span of data for microcystin concentrations in this lake. Microcystin is one of the toxins monitored in the state. And what the data show is that there is an increasing number of detections as well as the levels of microcystin in the water are increasing. The advisory level for microcystins is also noted on this graph just for reference. So you see that in the past, at least the trend line was below that line and most of the samples, but starting in 2017, more and more of the detections are above the guidance level. A similar graph for Spanaway Lake, that's locally here where our university is located in Pierce County. This is a little bigger lake, 251 acres, and it's notorious for its toxic bloom events. And in this lake, you see even higher levels of microcystins, but the same trend that number of occurrences and toxicity levels are increasing over the span of this almost 2 decades of time. Another graph showing now all 4 toxins that are monitored by the state: microcystin, anatoxin A, cylindrospermopsin, and saxitoxin. And what you see here is for the same time period, the number of freshwater locations. These include lakes, ponds, reservoirs, and even some river reaches where monitoring has taken place. You see, I didn't point that out, that these data come from what we call the Northwest Toxic Algae Program. For those of you who are not from the state and not familiar with HABs, this is the state's opportunistic monitoring program. So this is an issue that's becoming more and more relevant in our state as well as nationwide, as shown in the literature as well. So in the state of Washington, these are the 4 toxins that are monitored. Microcystins and cylindrospermopsin are hepatotoxins, so they affect the liver. Anatoxin A and saxitoxin are neurotoxins. All of these toxins are primarily causing acute impacts, but they can also have chronic effects. And the health effects can be very drastic in some instances. Microcystins is by far occurring at the highest number of occurrences, so that's why you saw those previous graphs. We focused on that for the 2 lakes that I showed you. Just to provide a little more background on the guidance levels that are used in the state of Washington. The top part of the table shows the guidance levels for recreational water use, and the 2 hepatotoxins have EPA guidance levels, cylindrospermopsin and microcystins. The 2 neurotoxins don't have EPA guidance levels, anatoxin A and saxitoxin, but the Washington State Department of Health does have provisional guidance values for these toxins as well. And just for additional reference, you can also see the drinking water health advisory levels for anatoxin A. The state DOH uses Oregon guidance levels, borrowing from the neighboring state. So a little bit of a history for how freshwater HABs have been controlled in Washington. Again, for the benefit of those of you who might not be from here, the Washington State Legislature established what we call the Freshwater Algae Control Program in 2005, and the Washington Department of Ecology, which is our state environmental agency in Washington, is managing this program. Ecology, how we abbreviate this agency here, works with the Washington DOH they established together this monitoring program, this opportunistic monitoring program that I was referring to earlier in 2007. And they also work with local health jurisdictions, who in turn use these data to guide their public health advisories related to specific lakes in their jurisdictions. This program also funds the King County Environmental Lab. King County is where Seattle is located, that everyone must be aware of when you think of Washington. And this lab is conducting the toxicity test that results of which are then posted on the Northwest Toxic Algae website that is freely available to everyone. So you see very close collaboration between state and county level jurisdictions and organizations within the state. Most recently, Ecology also updated the water quality assessment listing methodology for the state to include cyanotoxins. And this is essentially the 303D listings mandated by the Clean Water Act. And this happened in 2024, so just last year. So after this brief introduction, let's focus on what our work entailed. Again, leading into the problem statement, here in Washington, because we have this opportunistic monitoring program, one of the issues is that this relies on someone seeing a scum on a lake, or a dog or a person being exposed to a toxin and experiencing some health impacts. So as you can imagine, this can lead to delays if there is no such occurrence happening in the detection of HAB events. And as the number of these events is increasing with climate change and increased anthropogenic impacts, it's really important that we develop tools that can help us monitor these events in a bigger picture way. So our research questions were, can we use newly available high-resolution remote sensing tools imagery to predict both the emergence and the evolution of these HAB events? And specifically, can we do that in small to medium-sized lakes that fall out of the range of what has been done in the past with similar tools? More additionally, in Western Washington, we have a lot of rain throughout the year, except for the summertime. And we were also questioning that will the cloud cover that occurs during those rainy times, will that be an impediment for making this tool successful? But when we look at the toxin data that showed us that most of the occurrences would occur during times when there is not too much cloud coverage. So we were hopeful. So I mentioned other efforts that has been done in the past and are documented in the literature. EPA SIAM method is the most well-known. The focus of that method is lakes that are large, greater than 500 acres typically. In Washington, we have almost 2,000 lakes, and only 8% of the lakes fall into that size category. Also, HAB issues, most of the HAB issues don't tend to be located in those lakes in the state of Washington. We have above 1,800 lakes, which is 92% of the total number of lakes in Washington, that fall into the smaller size category of 30 to 500 acres. EPA SIAM data cannot resolve these lakes, but our method can. So this is where we come in with our innovation. Our overarching goal was then to use specific data products from 2 satellite constellations to investigate these small to medium-sized lakes, the 30 to 500 acre size within Washington. One of the satellite constellations was the Sentinel-2 Level 2A data product package that we used. This was specifically to capture water quality indicators for chlorophyll, turbidity, and phycocyanin. And we also tried Landsat 8, the collection 2 data product, to extract water quality indicator for temperature. You, of course, need to validate your tools. So we used historic field data, and we also implemented our own field sampling program to collect water samples and help us validate and verify our method. So you'll hear more about the details of that throughout this presentation. And I'll pass it on to Gopal now.
Thank you, Michelle. Um, I'll just provide a little bit of background on some of these satellite data products that we have used in the project. And just to start off, this is just a, a photograph of various optical images of water that's from a from a publication, and the optical color of water is commonly used to understand the physical, chemical, or biological content in the water column. And this is very common in, especially in the marine conditions. And if you switch to the next slide. Yeah, and one of the ways this is done in the Sentinel-2 Sentinel-2 satellite is that the surface reflectance off of the landscape is captured by what's called this multispectral imager, and different wavelengths of light that's captured is responsive of different parts of constituents in the water. And so our focus was primarily on, for especially for Sentinel-2 satellites, primarily on chlorophyll, phycocyanin, and turbidity. Chlorophyll being the cellular pigment, and it has a certain wavelength where it has it provides that signature. And the same thing with phycocyanin, which is a cyanobacteria specific pigment with a specific absorption feature, and turbidity, which is basically a scattering parameter caused by suspended particles in the water. So if there's a lot of suspended particles in the lake, or we could should be able to detect that. So yeah, next slide, please. So Sentinel-2 constellation consists of actually three satellites now: 2A, 2B, and 2C. The first one went up in 2015, the second in 2017, and the last one actually happened last year. And it is actually designed to replace one of the older ones because it has a 12-year life cycle. We did not consider the third data satellite in our process because it was late in the game, and also there was a delay in actually showing up the data showing up in for use. Currently, the revisit time is about 3 days, but we expect when we worked on it, most of it was between 3 and 5 days. Next slide, please. The multispectral imager has these different bands that are reflective of different constituents in the water, and there are many bands that it provides data for, and we chose the 5 bands that are of interest for us based on literature survey and some of the published algorithms for these. So those are what I have pointed out in this particular slide. Slide. And the water quality algorithms we implemented are peer-reviewed publications have provided these information, and we specifically used one product called the Level 2A product within the Sentinel-2 satellite data products, which is one of the higher level data products that filters out a lot of the processing that is necessary for lay people like us to use. So it's really useful because it's a easier implementation for us to work through with our workflows. So we implemented these kind of 5 different algorithms and then we chose a time frame of 2019 to present because the level 2A product was started to be distributed only starting in 2019. There are ways to actually get data from even the earlier years when the satellite was up, but we did not do that because that was again another advanced step of processing the data. Next slide, please. The Sentinel-2 data is distributed in terms of geometry, and there is a tiling geometry that encompasses the whole Earth. And I have just provided just the tiles that are fall within Washington state boundaries, and there are about 28 tiles, and each tile is roughly 100 by 100 kilometers. And just to give you an idea, a single data product that constitutes all the data for one pass for one tile was anywhere between I would say a gigabyte to 1.5 gigabytes. And so you can imagine if the satellite is flying every 3 days, roughly 160, 180 days a year, and for a single tile, you were talking 180, 200 gigabytes per tile per year times 28. So you can imagine the level of data that is necessary to be processed. So next slide. So we created a workflow, and one of the important pieces of our workflow was that we wanted to use this as a teaching tool to provide students to be able to understand coding, be able to implement it, and perhaps document the code in a way that we can use it further along. So we chose to go with Python programming language and open source libraries for it. And the workflow generally involves understanding there is a cloud mask which provides identification of all the pixels that have been identified as cloud within the image, and then there is a non-water mask, and there's a water mask. And so we have to take these different slices of data, perform the band algebra related to extraction of water quality indices, and then we export them out as raster images and extract. And at that point, we extract individual lake data, and then we process them further down for like adding our own data or prior monitoring data and collecting and synthesizing the data. Next slide, please. We, as I was mentioning, we processed nearly 1 terabyte of imagery for the time period between 2019 and 2024. Water quality indicators were like for 25 lakes in Snohomish County and 8 lakes in Pierce County. And as we were talking about that, not all the prior monitoring data was sufficient to fill all our understanding of the data. So we went ahead with some field sampling, and I'll let Jim take over from here.
Thanks, Gopal. Hi, everyone. So our field sampling campaign last year happened from June to September. We aligned our collection dates with the satellite overpass so that we would actually get data on or measurements on the same day as the overpass. A bunch of volunteer data had been collected, but it was hit and miss as to whether it overlapped with the satellite days. We focused down here near UW Tacoma where our students were. So we did 8 different lakes sampled on a regular basis during that time. We went out and took grab samples for chlorophyll A and turbidity, which we measured back in the lab. And then we had a YSI instrument calibrated to use in the field for chlorophyll A, phycocyanin, and turbidity. I would say, because this is going to go with the data later on, is we focused only on days where we had less than 50% cloud cover for processing that data. Next. So we looked at 3 different ways to compare, to ground truth our data. So we looked at comparing our measurements with the corresponding pixel from the satellite that covered that same area on the lake. So that was one way. We also looked at taking a lake-wide average of the satellite data and then comparing that to our in-person data collection work. And then finally, through another band of way of doing this is to take the 9-pixel average, so the 8 pixels that, and the one that, the 8 pixels that surround your pixel where you collected your data, plus yours, to give sort of a more localized but still average value for where you collected those data. So we'll walk through each of those. So first of all, looking at the pixel to pixel comparison, you can see a pretty poor regression that we see looking at chlorophyll A or phycocyanin and the satellite values on the y-axis. And these satellite values, by the way, have no concentration value. They're just indexes that come from the numbers that the satellite spits out. So you can see some pretty poor correlation between these two, which may have to do with the fact that the days overlap between satellite pass and when we collected this, but the times do not line up and other things. You can see some sort of variation in the theme. So pixel to pixel doesn't seem to be the way to go. Overlapping the single pixel with your ground truthing data does not seem to be the way to go. This is also, by the way, looking at 2019 data, because in this case, we're looking at a YSI that was deployed from Pierce County to have a whole lot of data in Spanaway Lake. So this is 2019 sort of YSI data compared to the satellite. Next, please. And then this is ratcheting it out a little bit. So this is taking a lake-wide average from the satellite data on the y-axis, and then again, that YSI data for chlorophyll and phycocyanin. You see a much better correlation. It's still not perfect, but a much better correlation than what you got from comparing just the 1 pixel to where the YSI data was. Next. And then finally, this is looking at that 9 pixel average, and the R-squared value goes up even higher. So that sort of immediate area average seems to be a really good approximate area to compare to your YSI data in this case, both for phycocyanin and chlorophyll. So it shows a good correlation between the two. Next, please. All right, and then stepping out again, this is now looking at 2019 to 24 data for microcystin concentrations themselves in the lake that were collected by Pierce County, and comparing that to an index that Gopal will talk a little bit more about later, that takes the satellite values and turns those into sort of an action matrix, if you want to think about that way, of a 1 to 6 scale. So you'll see this come up again. But what you can see is that there's a good agreement between an increase in the satellite chlorophyll values and microcystin values that fit more of a exponential curve, with some noise in there, again, as mentioned by Emese, that there was it depends on how you're collecting those data. So sometimes you go and collect your microcystin levels at the most concentrated spot in some place, which doesn't necessarily correlate with lake averages that we're using for this comparison. Thank you. Next one. And then this is our own data. So this is spot grab samples for chlorophyll that we're looking at here from the lakes. And the one on the left is looking at the lake-wide chlorophyll average, and the one on the right is that 9x9 pixel. So you can see that this the single data point that you get out of doing grab samples isn't the best at actually reflecting what's going on. The previous examples that we showed were a daily average of continuously monitoring YSI probes. And so that gives you a better average to compare to your satellite average for the day, or satellite aerial average for the lake and for the 9x9 pixel than a single grab does. It also makes it harder in the 9x9 pixel grab because you're on shore, and therefore are just offshore. We weren't in a boat, and that makes it more difficult to get that kind of agreement. As well as a single grab sample doesn't correspond to the exact time that the satellite flies over. This is looking at 2024 data. Next. So to kind of step back, so it turns out at the longer time scale, you do get a better picture from those single grabs than you do at the sort of smaller time scale. So in this case, this is volunteer data that's collected over about 5 years by Snohomish County and their volunteers on Lake Ketchum. And you can see more agreement between the chlorophyll values coming from the back process satellite data compared to the actual values collected by volunteers on those lakes. And these don't necessarily, the grabs don't correspond exactly to when the satellite passed over, but it gives you an idea of how you do see agreement between these two things. It's just hard to compare on a tighter time scale because of this variation from time to time. Next, please. And then again, looking at, sorry, the first one was chlorophyll A. This is for phycocyanin. You see, again, this agreement of high values early in the time frame, and then going down after that, after they did some lake treatment. So again, more agreement at the longer time scale with these grab samples. But overall, it seems that at least on the more immediate time scale, going after probe data that's continuously monitoring and out in the lake might be a good way to go. But this is also a great way to work with volunteers to maybe collect data on the same days as satellite passes as a proposal going forward. Next. I think it's over to you, Gopal.
I'll quickly go through this part, which is, I think, kind of one of the big takeaways of our project, which was that we developed this, what we call as a lake-wide water quality condition a conceptual model for it, which was considering what Jim mentioned about this sort of wide variation seen in lake pixel data. So we decided that we wanted to do a pixel classification, which was to try to group pixels that have similar values. And so we ended up doing it in a 6-level pixel classification scheme, and we did it by binning them in a log scale. And after trying multiple ways, this was the best option. And we implemented this and developed what's called a numerical area weighted average value and also maps. And you can see the map here as an example for Spanaway Lake on 2 different days, where you can see the texture in the map is kind of showing you on the southern side of the lake there is higher chlorophyll, which is commonly occurring when the bloom begins. The condition starts to appear in the southern end of the lake, actually. And then the 6-level classification scheme basically says number 1 will be open water, and number 6 is, the whole lake is all full of heavy scum. And area weighting, this binning allows us to do the area weighting easily, and so that's the result I wanted to show. Next slide, please. So I want to do this as a little bit of a story, and so 2 different ways, and I want to do it for a lake called Ohop Lake, which is in Pierce County, in eastern Pierce County. It's a narrow, skinny lake just north of Eatonville, if you're familiar with this area. About 220 acres, but it's has this kind of like a narrow geometry. And so we implemented these 2 different ways of doing it using a map, like tracking bloom conditions using a map, as well as this area weighted warning level tracking. So yeah, next slide, please. Thank you. So I have a couple of slides showing these kind of maps. So the year is 2019, and the dates are up on there, August, most of it, all of it in August. And you can see the dark red marker pointing to where the health department was sampling during this time period. And not all time periods coincide with the time when this health department was sampling, but I just point, if it is different from the date the data is shown, I pointed it to the date there, and you can see that there is a little bit of open water on August 6th, and then it starts to increase in chlorophyll, and by August 31st there is, most of the lake seems to be really high chlorophyll levels, and technically it'll be like level 5. So yeah, next slide, please. And as we go into September and October, there is probably a lot of concern on the part of the lakeside residents, and they kept insisting on sampling. And then since they started getting high hits of microcystin, you could see that it starts to top out around at 15.2 microgram per liter on September 30th, or the 25th of September, and I have it pointed on the map for the September 30th, and you can and on October the 10th you start to see this really high scummy pixels with seemingly noting scum in there, showing up in the northern end of the lake. And then if you go to the next slide, you'll start to see that it starts to wane because dry season has ended and we start to see rain here. And there is some high chlorophyll in the northern end and a good amount of scummy areas on the southern side of the lake. And then there was still some concern about microcystin, and it was sampled on November 8th, but that was the last sample that was collected. And after that, the satellite data continued to show heavy scum in December and all the way into February, when early February, when it showed a fair amount of clearance and some scum appearance on the shoreline. Next slide, please. So that was kind of, talking about it as a map, kind of a map, a story map, so to speak. But our focus was on providing tools for public health practitioners to be able to use more information that they can use it as a way to decide on how they can manage the lake. And so this is basically the exact data that I just showed you as a map, but in terms of a time series, because our area weighted kind of warning system provides this sort of ability to do this. So on the left axis is chlorophyll or phycocyanin level, which is the 1 to 6 level that I was talking about. And then on the right side is the microdistance test that the health department is doing, which would be with the red markers. So you can see that as soon as the as soon as it hit August, late August, when the lake levels for microdistant for phycocyanin and chlorophyll showed started to show go up to 5, and it remained so until mid-November, and that's when it started to wane. And then the waning happens and goes on until like early February or mid-February, and then it reduces to well below 3. And this is a way you can see that this sort of a way of looking at the data using remote sensing provides a lot more context and a lot more information than sampling the stream or sampling the lake provides. And so this was one of the takeaways of our work. Yeah, next slide, please. And just to add a quick note about what we worked on with our temperature data, we worked on Landsat data. Landsat has a collection tool called Analysis Ready Data Product, which has a thermal band that can be used to look at temperature or surface temperature of lakes. And we used this and we did some pilot scale testing of the data, and it looked good, and we were going to work on it. But there was, in terms of the tile geometry and in terms of the workflow necessary for it, since we were so stuck on having using Sentinel-2 data, it turned out to be a really heavy lift for us to try to incorporate this different geometry into our workflow. And so we know that it does work, and we know that it's something we would like to do as part of a longer term sensor-based monitoring, and use that as a way to understand, add temperature into our model. Next slide. I think this might be the last. Yeah, if you want to take this from now on.
Yes, I can take. So in conclusion, we achieved many things. We developed a successful tool, this multispectral satellite imagery. This particular product from Sentinel-2 satellites is a good tool to monitor these smaller lakes that prior tools were not able to do. We were successful in extracting indices for chlorophyll A, phycocyanin, and turbidity, the first two of which worked really well in predicting the emergence and even the evolution of these bloom events. Turbidity didn't show us good correlations because there is more interference with turbidity, but we were expecting that chlorophyll A and phycocyanin would work better to begin with. For the temperature data with Landsat, again, it was very difficult to reconcile with the workflow that we had with the Sentinel-2 data. So we really would need to develop a separate workflow for that, which turned out to be a bigger effort than was possible in the current project. As potential future work, we do think that that would be one area to develop those temperature indices, again, with a completely separate workflow. And then there is a lot of opportunity to really work with collecting more field monitoring data, especially data that's aligned with the satellite overpass areas, because we found we did much more than what we show here. We looked throughout the state and looking for data, and there is not enough comprehensive data that's available, especially when we start to talk about automated collection methods. So we do see collaborations. If any of you on the call, or if you know people who would be interested in doing this work in future projects, please reach out to us. We would love to have a chat about that. We also think there is more potential for developing those regional scale models if we have the data. And just in the interest of time, I did want to point out here that broader impacts were extremely important for our funder and for us as well in this project. So in addition to this having a direct relevance to public health guidance development, we did have a quite significant impact in research and education. We established an interdisciplinary collaboration between our environmental science and civil engineering programs. We had undergraduate students working on this project for whom it was really a transformational experience to learn about these methods and apply them. And another cool thing we do on our campus is we do course-based undergraduate research projects, and which means that the whole class, all students in the class benefit from research, not to the level as our individual research assistants, but to some extent. So I had a project like that in my class, and students enjoyed working on that. So with that, I would like to open it up to questions.